In this video we're going to have a look at the Bronsted-Lowry theory of acids and bases and compare it to the Arrhenius theory which we learnt about in the last lesson. The Bronsted-Lowry theory of acids and bases was developed after the Arrhenius theory, and that is because there were those things that Arrhenius theory could not explain. For example, it could not explain why ammonia is basic because according to Arrhenius theory, bases needed to have OH in their formula and ammonia did not. So this theory was an expansion on Arrhenius theory that could account for all of those things that Arrhenius theory could not. Alright, there are three main ideas which make up the foundation of Bronsted-Lowry theory. Acids under Bronsted-Lowry theory are considered to be proton donors, and bases are considered to be proton acceptors. Now I am using the word proton here, but one thing that you should keep in mind is that a proton is the same thing as saying H+, because when you have hydrogen atoms, they have one proton and one electron. If it is H+, then it has lost one electron, which just leaves one proton. So when I say an acid is a proton donor, I mean it is a substance which gives off H+. Bases are considered to be proton acceptors, which means they are substances that can accept H+. Now this includes hydroxide ions, because hydroxide ions can accept a H+ to make H2O. But there are also other substances like ammonia, which can accept protons. One key thing which came through Bronsted-Lowry theory was the recognition that some substances are amphoteric. The word amphoteric means that a substance can either act as an acid or as a base, depending on what it is with. So this means that one chemical substance, for example water, can sometimes be a proton donor if it is paired with something which is basic, or water can be a proton acceptor if it is paired with something which is acidic. We're going to have a look at some examples later which show examples of amphoteric substances. First off though, let's have a look at some equations using Bronsted-Lowry theory. Now you notice that in each of these equations that I've set out, there are two things. Because if you have something which is a proton donor and it is donating a proton, there needs to be something else to accept the proton. The proton has to go to somewhere. So in each of these equations, there is one acid and there is one base. To figure out which thing is the acid, look for the substance which has lost a H+ charge. So you'll notice that the number of hydrogens will decrease by 1 and the charge will become 1 more negative. In this case we've got H2CO3 here and it ends up forming HCO3-. So we can see it's lost a hydrogen atom, it has lost a positive charge. So it has given away a proton, it has given away a H+, and that means that this substance is an acid. If the H2CO3 is a proton donor, it must be donating its proton to something else which accepts the proton, and that means the other substance, in this case the H2O, is going to be a proton acceptor or a base. We can see that it's a proton acceptor by looking at what happens before and afterwards. So we start off with H2O, we end up with H3O+, so it has gained a hydrogen atom and it has gained a positive charge. So this means it has accepted a H+, and therefore it is a proton acceptor, it is a base. Alright, our next equation, we start off with ammonium ion, which is NH4 positive. This ammonium ion reacts with hydroxide ion. The ammonium goes from NH4+ to being NH3. It's lost a hydrogen atom, it's lost a positive charge. This means that this substance is a proton donor or an acid. The hydroxide started off as OH-, it turned into H2O, so it has gained one hydrogen atom, and it has gained a positive charge which took it from -1 to 0. Therefore, hydroxide is a base in this equation. Example number 3. We have a hydrogen phosphate ion, HPO4 2 negative, reacting with CH3COOH liquid to make H2PO4 minus and acetate ion. The HPO4 2 minus has changed into H2PO4 minus 1. So it has this substance has gained 1 hydrogen compared to the original, and it has gained a positive charge because it went from -2 to -1. Therefore, this is a proton acceptor, and this substance is a base. The CH3COOH liquid changed into CH3COO minus is lost a H, it has lost a positive charge, therefore this is a proton donor or an acid. Finally, we've got NH3, which has changed into NH4 plus. It has gained a proton, therefore this substance is a base. And we've got HCO3 minus, which has lost a proton by changing into carbonate, is a proton donor or an acid. It's really key that whenever you are trying to show something with Bronsted-Lowry theory, that you show that these reactions involve both an acid and a base, where the acid has transferred its proton to the molecule that is the base. Finally, I want to show some examples of amphoteric substances. So remember, these were the ones where a single substance can either act as an acid or a base depending on what it is paired with. Our first example of an amphoteric substance is going to be water. In the first case, we've got HCl plus H2O making chloride ions, and this is called the hydronium ion. So we had H2O as a liquid, and it forms H3O plus. So this substance gains a proton through this reaction. It accepts a proton. It is therefore a base. However, if you take water molecules and this time you mix them with ammonia, NH3, instead of hydrogen chloride, the H2O ends up turning into hydroxide ions. And in the second equation, water has lost a proton. So therefore in the second equation, it's a proton donor, it is an acid. So this is saying that depending on what you mix the water with, it can either act as a base or it can act as an acid by either accepting or donating a proton. Another example of an amphoteric substance is the hydrogen carbonate ion. In this first equation, HCO3 minus has gained a proton when it turned into H2CO3. So therefore this substance is a proton acceptor, which is a base. In the second equation, the HCO3 minus has been mixed with hydroxide. It has donated a proton, and therefore this substance is an acid in this case. So once again, depending on what substances you react with the hydrogen carbonate with, it can either act as a base by accepting a proton, or it can react as an acid by donating a proton. You should also be able to recognize that in each of these equations I did, that the substance which has been reacted with it must be the complementary either acid or base, as there always must be one acid and one base in each equation.